Welcome to today's seminar. Thank you for coming out. And I'd like to introduce Dr. Kanchan Maiti. He is from LSU, and we actually go back quite a ways. We were graduate students on our very first research cruise in 2004 in the Sargasso Sea. Even better, we managed to be bunkmates, and we were on opposite shifts, so we never really had to, hear the other one snore. Which was lovely. But Dr. Maiti did his undergraduate in the University of Calcutta in geology, and he got his master's at the Indian Institute of Technology. And then he came to the United States and worked with Claudia Benitez Nelson at the University of South Carolina. And then he went up to Woods Hole Oceanographic Institution after earning a postdoctoral fellowship and worked with Ken Bissler. And Billy was the radium guy?
Yeah, before in my days.
Okay. And Ken Bissler. And then in 2010, he went to LSU, and we have bumped into each other so many times at meetings that we said we should work together. And so Kanchan is going to show some of the stuff that he's done that has facilitated some of our collaborations. But he's also been won awards at LSU for teaching and excellence in undergraduate teaching, a couple different awards, Rising Faculty Award, Excellence Award, and then he has just finished up a couple of years as a rotator at National Science Foundation Chemical Oceanography as a program manager. So if you want to know the secrets of NSF Chemical Oceanography, this is the man you need to talk to. But his talk today will be titled Seasonal Transport of Dissolved Inorganic Carbon Across the River-Influenced Shelf of Northern Gulf of Mexico. And may you please welcome Dr. Kanchan Maiti.
Thanks. Thanks, Jeff. Thank you, everyone, for showing up. I know I myself have been guilty of just zooming in, so I really appreciate you coming down here for the seminar. It's always the best way to give a seminar. So yeah, me and Jeff go a long way, and I think we have quite a few graduate students. One thing I can say, we do not do what we do today when we first met, right? And so I think that's important as graduate students that you evolve. So what I'm going to show today is more coastal work. I never worked in the coast before I came to LSU. The shallowest water I worked and before coming to LSU was, I believe, 1,000 meters or so in the Arctic. And then I'm working in 50-meter water depth. And this talk is all about 50-meter water depth. Because as we all know, Louisiana shelf is actually quite shallow and wide. And there's a lot of carbon that is coming down from the Mississippi River, from the wetlands. And so my talk is about what is the fate of that carbon as it comes off the continental shelf. Okay, so first slide, why should we care about shelf carbon cycling? So there are a number of reasons to look at shelf carbon cycling. I think I must say this is one of the areas we haven't really paid a lot of attention. We always looked into the biological pump, we looked into wetlands, but this transitional zone between these wetlands and open ocean, these shelf areas, they can be a huge place for sequestration or addition of carbon. And that is evident, actually, if you look at the recent paper by Major Raymond, which came out last year, it showed that even after so many years, we cannot balance the global carbon budget, okay? And the two problems that is there in the global carbon budget is air-sea exchange and lateral input of carbon coming in from continental margin. So those are the two biggest uncertainties. And what is a place that we should look for if we are thinking of lateral transport of carbon across the continental shelf? There's no better place than Mississippi River shelf, because you have wetlands that are decaying, that are losing land and losing carbon. You have Mississippi River bringing in so much carbon. So there is the place to try to tie in the budget. So that's what this shows. The slide kind of now narrows down to what we think is happening in the continental shelf. As you can see, that we have this river plume on the top. You always get some kind of stratification. The river usually is super saturated with CO2, and it also brings in a lot of carbonate. Then you have photosynthesis going on, you have productivity, and you have this big recycling of DIC, POC, and organic matter as the water flows out. And it can also lead to hypoxia and ocean acidification, and that is a project that I've been working on, but we will go into that today. And we can see right now the estimate, I mean, it's not a very robust estimate, but right now the estimate of carbon moving from continental region into open ocean is about 1 gigaton. I believe that number is on the lower side, because there's so many areas we haven't really looked at. And we can see the wetlands also sequester a lot of carbon. And on a global scale, the ocean is sequestering about 2.5 gigaton of carbon. So you can see how easily by changing this number, we can change the entire budget of the global carbon cycle. So as I said, on a global scale, we have uncertainty in our carbon cycle. So Northern Gulf of Mexico is no exception. Even with the amount of work we have done in Northern Gulf of Mexico, you can see there's way more question marks than numbers in that slide, right? I mean, we don't know how much carbon in any form, DIC, which is dissolved inorganic carbon, DOC, organic carbon, particulate carbon, all with red question marks, meaning we really do not have a good handle on what is even coming out for one region, which arguably is one of the best studied system in US, especially after BP oil spill. We spent so much money looking at all the different aspects of Northern Gulf of Mexico. So, and we can see at the end, this is kind of what is coming in from the river, question mark, what actually gets sequestered, what goes out to the deeper shelf, and then what goes out to the open ocean. Most of them are a big question mark right there. And we're not even talking about this benthic flux exchange. That is another project, another day. Okay, I'm still working on it. But the idea for this project comes from this fact that we really need to have a better understanding of lateral transport of carbon across these Mississippi River influenced shelf, because we can argue that the Mississippi shelf, the river is putting in so much water and there's so much advection moving outward, it should transport a lot of carbon. So for this talk today, I'm only going to concentrate on DIC because that's one of the trickiest one. Dissolved inorganic carbon is sum of 3 species, right? That's the PCO2, that's this gas CO2 that is in the dissolved in the water, the carbonate and the bicarbonate combined. And the reason we club them together is because they can interchange as a function of temperature and alkalinity, right? So that's why if we're trying to look at dissolved carbon, we have to look at all these 3 species together. So what do we know about Gulf of Mexico carbon budget? So what we have done is we have really looked at this Northern Gulf of Mexico and Gulf of Mexico as a whole in terms of a simple box model. You can almost think of it as if you have taken the oceanography courses. At some point, you have learned about residence time, right? It's a flux in, flux out, and what is in there, right? So you can use that same concept to figure out how much carbon is going in through the loop current, how much is coming out. The difference have to be coming from Gulf of Mexico, right? It can be from river flow, it can be from wetland, it can be from air-sea exchange, whatever be the process, the delta between in and out has to come from here within the Gulf. And we can see our air-sea exchange, we have a reasonable handle on that. So what people have done is they looked at this delta, what is the carbon coming in, inorganic carbon, what is the carbon going out, and then they tried to model the air-sea exchange, and the difference is what we attributed to lateral flux, coming from the river, coming from wetland loss, whatever it may be. It's kind of like a black box. That has to be the difference. But what if we do not know this number very well? Then okay, I should back up a bit. And this river input actually takes not just river input into place, but also the wetland that is breaking up and releasing carbon. So this is not a real river input. It's basically the difference between this and this. So there lies the problem, because it is kind of like a black box number, which is catch all, just the difference between those two. So, and why I think that may not be the right approach is because, sure, river is a big player here, right here, that brings predominantly carbonate and bicarbonate. But we have this entire area along the Louisiana coastline, everything in red, that is projected to disappear in next 50 years. That's the amount of land loss we're talking about. Right now, we lose about 25 to 35 square miles or 25,000 acres of coastal land every year. And you can see this island right there in the middle. That's no island, that used to be a marsh. So, and here is another one. You can see, so once we went out in the marsh, we put in this stake there. It's basically a PVC pipe and at 5 meters interval, and you can see what was at the margin. So this pipe here is actually installed right at the marsh edge. Next time we went back there, a month and a half later, we have lost 1.5 meters of land. So you can see how much land we lose in 4 months. And right now, 80% of the coastal wetland loss in our nation is happening in Louisiana. So if we scale this up, think of wetlands, these have 10, 20, 30% organic carbon in them, organic matter in them. Where is that organic matter going? If we are losing the marshland, it got to go somewhere, the carbon that is trapped there. And that carbon was there, preserved there, because the conditions were reduced, right? That allows carbon to be preserved better. If you expose them to toxic environments, you're going to remineralize them pretty quickly, either as DIC or CO2 that just fluxes out of these estuaries. So that's kind of what got me into this project. Like, okay, we really need to understand what is happening to this carbon. And here you can see just a basic back of the envelope calculation that I did for only one day. So we did this for this one Barataria bear, and you can see on average there's 19 milligram of carbon per centimeter cube. So we're talking about this tiny cube that is 90 milligram of carbon. Just for this basin, by multiplying how much wetland we are losing and the average concentration, we are losing about 1.75 million tons of carbon per year from this one bay in Louisiana. So where is this carbon going? That's basically the fundamental thing we really need to understand. And if you look at almost all global models, they kind of leave it as this kind of gray area. Most of the models cannot incorporate them because this is their boundary condition. Most global models have their boundary condition set at this, and it does not change because these are all not dynamic models. So you have to kind of include that. If you want your boundary condition to change, the model numerically would probably not work. It will blow up. You need a lot more complicated math to do that. So this was kind of what we wanted to show in this project is how much of this carbon is moving out, really. So here is a very simple simulation that we did for the same bay, this bay right here, where we are losing 1.75 million tons of carbon every year. And what we have here is we have kind of a simulation which doesn't include land loss on your left, and we have a simulation on your right which include land loss. This is very rudimentary model, so there's a reason why it is so rudimentary, because we don't have any data to calibrate this model. So any model that is not calibrated, I probably shouldn't even be showing, right? It could be anything. I can make it 1000 ppm if I want, but it looks reasonable. The number looks reasonable. We now have some numbers since the last year or so, and what you can really see is without land loss, with land loss, your red areas, your warmer colors are more. At least that is quite apparent. That means what it is suggesting, and if you keep looking at it, you'll see it really gets warm colors during July. Right there. And what it kind of indicates, and based on what we know, is as this organic matter gets released from wetland loss, with the high temperature in summer, they get remineralized very quickly. So you have big production of CO2, and that's what we are capturing. But it does not capture the DIC part, because DIC part is way more complicated to capture. PCO2 is very simple to model. But that kind of gives us an idea that yeah, indeed, it can happen. And what we think is a majority of the carbon probably is lost as dissolved inorganic carbon rather than CO2 fluxing out of the water. Okay. So against that backdrop, we got this funding from NASA to do this work because we want to incorporate this aspect of carbon input into the ocean from continental margin. We call it the carbon leakage from the continental margin because right now it is kind of leakage. And Louisiana, it turns out, has this perfect contrasting area to work on. It has this only place in entire Louisiana where there is land building, and some here, and these are all actually because of artificial work. Basically, the Army Corps is putting in sediments there, more of a dredge, really semi-natural place. I would say, I wouldn't say it's completely natural. I'll explain it in a second. A semi-natural way where we have land formation in entire Louisiana is the Wax Lake Delta of Atchafalaya River. And it was actually quite by accident. And if you look, if you follow this river line right there, it's a straight line, which kind of tells us that's not natural. So somebody actually dug up this canal, and it's a really deep canal. This outlet canal is about 70 feet deep and 150 feet wide. So it's a really, and it's basically like a pipe flow of water. And they did that to remove some of the water from the Atchafalaya River and divert it to save Morgan City right there during flood time. And when they did it back in the 70s, people didn't know the consequences. What it did, because it was like a straight flow of water through the pipe, it deposited, it dumped all the sediment it carried and formed this delta. It was an unintended consequence, but that grabbed the attention. And now what Louisiana Master Plan suggests is they want to do more of these to save this area by diverting Mississippi River sediments right here. Something like this, where we put dredged material, is actually very carbon intensive. I mean, imagine if you have seen one of those dredgers, they use million tons of diesel, right, to get the dredged material back on land. So using the river directly to piping the sediment by cutting in these kind of channels might be one way to save the coastline. But nevertheless, we have this area for 30, 40 years where we have this tiny land, tiny delta that is forming, kind of like our mesocosm, right? Where we can see a delta from day one as it forms, as it evolves, not just in terms of land, in terms of vegetation, in terms of the carbon content in the sediment. And on the other side, this whole red area here, that is one of the oldest delta low for Mississippi River, and it's sinking and it's losing land like anything. So now you can imagine there's a perfect stage to look at two very different deltas within the same system, right? Same temperature doesn't vary, but one, we still have land forming, one where we're losing land, one that has a lot less organic matter in their sediment, one that has a lot of organic matter in their sediment, about 30% here versus about 10% here. So we have these two very different systems to look at, and we decided to figure out how much of this dissolved inorganic carbon actually gets transported from margin to deeper shelf. And that's what led us to these two hypotheses. So what we thought is that this Wax Lake outlet, that is the almost artificial delta that is prograding, because it dumps water into a relatively shallow shelf, the shelf here is about 5 meters for a long period, as you go out. Versus this area, actually the shelf, if you look here, right here, you can see the contour lines are much closely spaced. So it gets deeper much faster, whereas here it's much shallower. So the idea was, because the Wax Lake or the Atchafalaya River, they're basically discharging water into the shallow shelf, they would allow more oceanward transport of DIC compared to this area, which doesn't have an active flow of water. So it's more passive. We have this diversion called Davis pond that trickles in water compared to these outlets is a lot less. And then the other idea was, other hypothesis we wanted to test is the magnitude of DIC we transport will be highest in June rather than in summer. That's because it's all driven by the river discharge, and the river tends to peak sometime in May, June time. So we expect that river flow will push the carbon outward more for this area. So what did we do? So we timed our cruise well. So we timed them during high river and low river flow. And if you follow this track here, the red is your Mississippi River discharge for the year 2019. The green is the Wax Lake outlet. So here and here. So those two over here. And you can see there's a orders of magnitude difference. Obviously, Mississippi River is way bigger in terms of discharge. And when did we go out to sample? Right where it was high, right where it was going down. So I think timing wise, we got it. I mean, that is always a logistical problem, trying to get the ship at the right time, but we were fortunate to get it. And every time we went, we took 2 transits. I mean, I wish we could do more, but there's not enough ship time. So we did 2 transits for the Wax Lake, 2 transits for the Battery Bay, and we had a resolution of about 9 kilometers for Wax Lake because we wanted to cover all the way close to 40-meter isoback, which is much further out because it's a shallower area, whereas here it's much shorter. You reach 40 meters much quicker. So that had a 5-kilometer resolution. And the other thing to note, it turns out, science is never perfect. It turns out it's probably not the best year to go out because this year, the Mississippi River was in flood stage for a record 200 days. I mean, so probably all the data will show, I'm happy we got high numbers, but they may not be the right numbers on an average scale. On a decadal scale, they might be much lower, but it turns out it was a year of really record-breaking floods and river discharge. And that's why you see that big decline right there. So how do you measure flux? So there are 2 aspects to this work. One is, of course, we need to measure DIC, right? To get any sense of how much DIC we're actually transporting. The second aspect is how fast are we moving it, right? That's how we get the flux. You need a concentration, you need a flux, 2 things. So the DIC measurement is pretty straightforward. We have this completely ocean acidification protocol-based DIC analyzer. So it measures DIC to like 1 micromole or less accuracy. So we can measure it very well, but it's the challenge is measuring the flux out, that lateral flow. And for that, we have to fall back on my favorite things, which are radioisotopes, because radioisotopes always have a sense of time, right? Because they're decaying. So if you have X amount here, Y amount here, you know exactly how long it took that X to become Y. So you know exactly how long it took X to move from here to here. It's simple time scale and half-life. So that's what I used, and I went wild with it. We measured all 4 isotopes of radium, but I decided to tone down for today's talk. We'll only talk about these 2, 2023 and 2022-4, okay, for today's work. And that is because these have shorter half-life, which makes it easier to interpret the data. The longer the half-life is, the more complex, because you have to go back into the history, think of other currents, other things that can impact their distribution. So for this talk, we'll just restrict to these 2 isotopes and figure out how we can use these radium isotopes to determine the flux rate. Because if you can determine the flux rate, you know your concentration, you can figure out your flux. That's simple. But it's that flux rate, that is where the radioisotopes come into play. But before we go there, we want to check how the shelf looked like when we were out there. Am I too far from the microphone? No. Okay. So here are like some sample profiles just to kind of orient ourselves right here. And you can see this is from the Wax Lake Delta from June and September, salinity on the, and you can see this beautiful plume of fresh water on the top, right? Land, ocean, beautiful, really stratified, and it is way strongly stratified in June, makes sense, way more fresh water coming in. The stratification is somewhat lower by the time it is September because the river discharge went down, but nevertheless, it has this really nice stratification that makes our life simpler with a lot of the assumptions. Battery Bay, kind of same idea. We see this strong stratification in spite of no direct inflow of water. We still have this dye stratification to look at our flow, and it is not that prominent by the time it was September. So before we go to the radium aspect of how we utilize it, I'll just give you a sense of how the DIC measurement look like. And a little detour before we go into the flux is like what it all means. So you can look at the DIC, these are color coded for the 2 times we went out in the 2 areas. Wax like delta in June, bacteria bay, the degrading delta in June, then again the prograding delta in September, low discharge prograding delta, retrograding delta in September under low discharge. And you can see our DIC are pretty much evenly distributed, and which makes sense. We lose a lot of DIC because of the productivity. Productivity takes out DIC for the carbon fixation, and the range in the range of 2000 micromole per kg. Very little difference. And then we also did alkalinity. We're not going to talk about it, but I thought because we have a lot of folks who are interested in ocean acidification and impact on biology, I'll take a quick detour on some of the interesting data before going back to carbon flow. So we measured alkalinity because we could, why not? And we had a lot of undergraduate students who are interested in ocean acidification. Each of these samples takes about 30 minutes. So I have to say these students are amazing to measure these, a lot of patients. And we can see the alkalinity also was a little bit more variable seasonally than DIC, but they're very much in the similar range. And here is my detour from our carbon talk here. And what we can do is, all of you probably know that if you know 2 parameters in your carbonate system, you can actually figure out your pH or your omega or the saturation, right? Carbonate saturation. And so that's what we did, the aragonite precipitation. And what we looked at is, and one thing which many of you may not know is it's a slippery slope. It's great, it works really beautifully to calculate, but as a chemist, I would rather measure it than do the math because of all these uncertainty. When these, you can use this, if many of you are probably proficient with R has this beautiful C-carb module that you can use to calculate this. If you have alkalinity, DIC, temperature, and salinity, it will spit out your CO2 concentration, your pH, your aragonite saturation, all these things. But really, we have to be cautious about how we use that data because mathematically, really the pH and omega, that depends on this difference between alkalinity and DIC. And the smaller that difference becomes, the bigger is your uncertainty. And that makes these oddball outliers that you should not use. So if you actually believe in math, we would have really undersaturation. All these gray numbers, those are numbers we should not use, although they were spilled out by CCAR to look at the aragonite saturation. And same with salinity. When the salinity is less than 20, we just simply don't know the K, equilibrium constant for some of these things at low salinity. So we have to be careful about how we use this data. So we basically took this box out because we thought these are too sensitive to these parameters and we cannot use them. We have too much uncertainty. So we only use this box, these numbers where you see this beautiful linear relation, which it should, because omega is directly proportional to alkalinity and DIC difference. And it does follow that. When it doesn't follow is where our math and our data is not there. And even if we look at that data set, we can see right here that although for most of the time we had a value greater than 2, which is what typically people think is the aragonite saturation limit below which it can be stressed, most of the water samples were actually oversaturated, right, in terms of omega. But there are these oddballs that were actually undersaturated further out. And in fact, we looked at literature and we found that these are the lowest omega values that are reported for Louisiana in the last 10, 20 years, as far as we can go back. So, and that is probably due to the fact that the buffering of fresh water is a lot less, which makes sense because this is a year we had record-breaking fresh water coming into the system. So it broke the buffer, and that's why we started seeing these lower values. And we'll talk about this implication because we all know probably many of the rivers, they're going to increase their discharge, river discharge. So how does that impact the buffering capacity in the future? So that's kind of like a detour I wanted to take just to show how this data can also be used for many other things that we haven't really paid attention to that much, but that's something we're working on right now. Now we're going to switch back to figuring out our main objective, carbon export. We figured out already, we have a very good number about DIC for the shelf. The problem or the challenge is how do we figure out how much is moving out, right? For that, you have to read this book. Just kidding. Okay, so this is actually a really nice book. I haven't read the entire book, but it also says how people used to drink radium at one point. Awesome stuff. Okay, I wish they would sell these because my standard cost $3,000-4,000. Probably this would have been cheaper, right? But no, we shouldn't be drinking that. But radium is a really fantastic isotope, and there's a reason to use it in the ocean for a lot of different things. But there are challenges to using radium. And if you guys deal with samples which are 1 liter and think, oh, these are big samples, well, you want to do some radium, that's 60 liters for a single sample. We're talking about 3 carboys to get 1 number. And so we'll definitely it's a really challenging thing to collect so much water, and you can really do it in a coastal system. And it really takes a lot of effort to collect this data. And I just look at people who do nutrient. I'm like, oh, what, 10 ml, that's it? Oh, that's like waste for me. I don't even think about 10 ml when we're talking about 60 liters. But fortunately, the extraction chemistry is not that bad. So we kind of, what we spend time collecting water sample, we save by extracting radium in a very quick fashion. We simply pass it through these fibers that we can make in our lab. And that can scavenge 99% or more of the radium in this water column. So that makes our life easier. And then we can bring those fibers back, leach them out, and measure them in what we call a delayed coincident detector for the short-lived ones, and on a gamma detector for these long-lived ones. And then we can look at the data. So why radium? Why all of a sudden I want to use radium? So there's 2 very important reasons for radium. One, radium is like a natural tracer. So it's like a dye. And it is very importantly a conservative element. So it doesn't get removed by biology. So rivers have a lot of radium. Ocean does not have radium because their half-life is short. So the river, where does the river get the radium from? From weathering of rocks. So the weathering of rocks brings in a lot of radium. You dump it in the at the continental margin, you have a dye because you are so much radium, and the ocean doesn't have radium because all the radium decays very quickly. As you can see, these 2 isotopes have half-life of 3 and 11 days. And another important thing is because they have such short half-lives, it really allows us to see their change on a much, much smaller time scale. Like we can actually measure the difference within kilometer scale. And that means we can figure out the time that it took for it to move from place A to place B. Second reason, and third reason is these 2 radium isotopes, they're very different salts, but they're same element. So they will behave exactly same. They're conservative. They're not taken up by biology at all. Very, very, very little. And yet they have 2 different sources, which means we can validate our data independent. We have 2 tracer, not 1. I mean, if I show 1 tracer data, we might think, oh, is that tracer, all the assumption is correct or not? But if you have 2 tracers showing similar data, that really makes the data much, much, much more robust. So you can see the decay chain, radium-224, that's the short-lived isotope, 3 days half-life, comes from thorium-232. The longer-lived one, 11 days half-life, comes from uranium-235. And that provides us these 2 radium independent isotopes that we can use and look at slightly different time scale, 3 days versus 11 days, to understand this flux. So now the math part, how do we do that? So it's actually not that different. All you need to do is you go out, We collect samples along this transit, cross-shelf transit for radium isotopes. We measure them. We know the distance, plot them, concentration versus distance, gives you this beautiful, not always, beautiful linear fit. And what it really means, it is showing us the distribution of radium with distance. And what controls this distribution of radium over distance in the ocean is hidden in this equation. The rate at which radium is moving out, that is your KH or eddy diffusivity or mixing rate. Then your second derivative of concentration, and its loss due to decay. And because we can solve it, we solve this, and it has an exponential. If you take a log, it becomes a linear, right? That means this equation really defines the distribution of radium in the ocean. And here you have X as your distance, A0 as your radium concentration at 0 distance from the shore, and AX is the concentration at any distance, right? That's the equation. This is the same equation that we are getting here through regression. And even better, it has its own check. If these numbers are all over the place and we do not get a good regression, that means something is being missed when you're trying to do this. And what could be that? That could be flow of current along shelf, because in this equation, we do not have any way of incorporating along shelf flow. So obviously that we assume that to be 0, but we can check that. Is that a fair assumption to make? And it turns out if you get something as robust as R square of 0.9, which is definitely significant, probably the along shore component is not that important. I'm not saying it's 0, but it's probably not significantly important to make a difference. And once we do that, really the slope lambda, that is your decay constant divided by mixing rate, is this slope. That's it. So we can just simply compare this slope with lambda by KH. We know the lambda, decay constant of these isotopes are known. And we know we got the slope from distribution of radium. We actually got our mixing rate. It's a relatively simple process once we think of it, but we have to remember these assumptions. Okay, that we do not have along shore, significant along shore transport. Also, what is your layer of water we are talking about? So for this work, mostly we looked at, for this talk, I kind of put only the stratified layer, which I would think of as a layer that is not having much exchange with the rest of the water column. Because once you start going into the bottom water, there's a lot of other complications that we have to keep in mind. But given that we have a really strong stratification, we decided to look at the rate only at the stratified layer. So all the data I'm showing is from surface data, and we have exact same data for the bottom that I'm not talking about today. So if we do it for the surface, less complicated, and we get our mixing rate, and then we can go crazy with it. And so we have 4 transects that we did twice, so 8 plots, and we get a mixing rate for 8 of those transects right here. Okay, and this is for the shorter lived radium, 3 days half-life, and you can see, yeah, not all of them are good. Here's one that looks not so good, but in general, for both the 2 transects, so these are west and east for wax leg, west and east for bad area, and you can see we can calculate our mixing rates. Oops. And we can do the same for our radium isotope, other one, which is 11 days half-life, same concept. And you can still see that kind of relationship, and we can calculate another independent way of this mixing rate. And if you look at these numbers, 4,800, go back 4,000. So we see similar trends. They're not exactly the same because the time scale is different, but they seem to match rather well between these 2 independent traces. And so we can put this all together, all those numbers together, and look at what are the mixing rates we are talking about. And we can see at a first glance, like this is the western transit for June 2019 for wax leg, and eastern transit for For the June also, both the isotopes, the dark blue is our shorter lived isotopes, 3 days. And the lighter blue hashed one is for the longer lived isotope, 11 days. And the first thing that kind of pops out is the transport of water, this eddy diffusivity, dropped by roughly 18 times between two systems, which kind of makes sense. Our water discharge dropped dramatically between June and September, right? And both those two isotopes have similar range of KH, which is good. That means they seem to be verifying independently. And we can do the same thing for our Barataria Bay. Right here, we see, again, the first order, they're much, much smaller, right? The mixing rates in the range of 4,000 max, in the range of 1,000 here. Makes sense because wax lag outlet, as I mentioned earlier, it's like a pipe flow. We have this big water coming out straight into very shallow shelf, which means the water has to move unless you actually increase the sea level, right? Which does happen, but usually it moves out. Whereas in the Barataria, it's a much diffuse flow, much smaller flow, some impact of Mississippi River. So we do not expect as strong lateral transport. And again, we see that similar trend. Even in the small scale transport, it drops by the time it is September, not as dramatic as wax leg, which has direct input, but still, nevertheless, it does decrease a little bit. So then we needed to, I mean, this is the first time this kind of mixing rate has been determined using radium isotope for this area. So we wanted to check, like, are these even realistic? Does this make sense? So we looked into the literature and we did find that they're pretty reasonable, given what other people have found using very different methods. They use satellite method, they use these Lagrangian drogues and buoys to measure this lateral flow. And then we also put in some, we ran the ROMS model, very simple, with a die, just a simple something XY die, and see where they go. And we can actually see what it is really moving out, right? On a very basic ROMS model, it's not very very well calibrated, but you can see for the same time we have this water coming out, and they are moving out offshore. And so we felt like, okay, these numbers looks reasonable based on literature and based on a very simple physical model. And then comes the next stage. Okay, we still haven't reached how much material is moving out. All we have so far calculated is a mixing rate, right? So somehow we have to convert this mixing rate to flux, right? Flux of carbon out of the shell. How do we do that? So we can use this length scale equation, which basically relates the length of the shell to its mixing rate and time over which it occurs, otherwise residence time, right? So we know the KH, we know it for every transect, every season. So we can plug in that value. We know the length. We know wax leg outlet will sample for about 84 kilometers out. For Barataria Bay, about 57 kilometers out. So everything is known except your residence time. We can calculate residence time for every transect, right? And we can do that. And no surprise, is the inverse of what we saw. The more is the mixing rate, the lower is the residence time. It's inversely correlated, completely makes sense. And it kind of gives us a sense of how long that water is hanging out in the shelf, roughly about 22 days in the wax leg side, and during June, whereas it's almost 100 days in September when we have not that amount of discharge coming in. Similar idea again for Barataria side, the other delta, and we see a similar drop in residence time. So we can use that. And we also looked at other people who looked at residence time, and it seems like their KH value yielded close to our residence time. In general, it looks like they're in a similar range. So now that we have confidence, now we can use this residence time to calculate our flux, because really now it comes down to a simple box model. Because Going back to all the DIC we measured, right? We have measured DIC for the entire shelf, which means we can come up with an inventory for the shelf for every transect, how much DIC is there. That's our big box, right? DIC inventory. And what is leaving the box has to be divided by the residence time. So we know our residence time. So if you divide the inventory by the residence time, you get your flux. And that's exactly how we do in chemical oceanography. That's 101. How do we calculate residence time of all salts in the ocean? We do the reverse. We know the flux from the river. We know the amount in the ocean. We can figure out our residence time. We're just doing the opposite of that. We know our residence time. We know our inventory. We can figure out our flux. And we calculated the volume, multiplied it by the DIC concentration, and we got our total inventory using these numbers. And now we actually have a flux, right? So how does that look? So you can look at the flux. We're talking in the range of 10 to the power 9 moles per day. That's the highest value we got for June. And it dropped pretty much from there on, all the way down to less than 2 times 10 to the power 9 moles per day in September. It's much lower for Barataria Bay in the range of about half of it, roughly 6 moles, petamoles per day. And you can see it basically there is a 3 times drop in DIC transport between these two seasons. So we can take the average instead of using each transit, because that counts some of these. These are transits that are literally 40 miles, 30 miles apart. So we can actually kind of use those, average them out to get a sense of the entire area. So we can kind of take them together and we can figure out the average flux for these two different deltas. Wax Lake in blue, Barataria Bay in orange. And we can see I have proved one of my hypotheses to be wrong, right? And my hypothesis was this area, Wax Lake outlet, should be transporting more carbon. But you can see within significance level, they're very similar, right? So that's one thing that we didn't expect, but we have to keep in mind that two sectors are not equal. So if we start thinking in terms of per unit area, still we cannot account for the difference. So nevertheless, whichever way we try to dice this thing, our hypothesis doesn't hold. But we did look at the number in terms of other work that people have done based on mass balance. And what they found was that the DIC supply was about 3.5 millimole per meter cube per day to the loop current. And we are way high. So what is happening to a lot of that DIC? Photosynthesis. They're getting transformed to organic matter as they go and meet the loop current. So there's a lot of loss that is happening, but still there's a significant amount of DIC that is getting transported from the Louisiana shelf. So basically, we can say roughly about 10 times 10 to the power 10 moles of carbon is being is transported from the Wax Lake area, whereas for the entire shelf, sorry, in Louisiana shelf, and about 2 times 10 to the power 9 in September, up to 40 meter isobath. Also, we have to remember when I scale this up for the entire Louisiana shelf, I kind of have no data in the middle, so I kind of extrapolated it. That's again, we can only do so much. But we did capture the two most important areas, and so that's something to keep in mind. And also, we should look at what the current estimate of DIC in the loop current is on the same order. So we can see, and this is, we have to keep in mind, this I average from the annual estimate. So this is kind of like a more coarser resolution, and we're talking about only 6 months of the year here. So there are some differences, but we can see that Louisiana shelf is a significant source of DIC to the Gulf current. Bigger pictures, other things that we talked about, definitely the DIC, the alternative trend that we're seeing suggests that there is a weakening of the buffering in this area, and there's a significant change in mixing rate between these two seasons, so that's important. And also winds. wind can make a big impact on a lateral transport. So we haven't accounted for that in this work. That's something we have to keep in mind that can increase or reduce the flow of carbon. And even bigger impact, I think what is important for us to remember, as our Mississippi River discharge is supposed to go up by up to 60% by 2090, we can imagine that coupled with the wetland loss, we can expect more and more carbon flowing laterally into the deeper ocean. So that's something that we need to keep in mind, even for the long, big scale models as we go forward. And with that, I'm going to end, and I have to acknowledge Shelley. You can see she did the entire work. This was actually her master's thesis, and she was amazing. She actually worked at 15 feet of seas on a 40-feet boat, and collecting 3 of those for each of her samples. So that's a lot of work. So with that, I'll also thank other undergraduate students and graduate students who helped with this project, and the funding agency, NASA and Sea Grant. Thank you.